wonderful gathering that you arranged, and this is very appropriate that we are doing this for my teacher and my mentor, Professor C.R. Rao. I'm going to talk to you about an interesting area of statistics that many of you may not have heard of. It's about measuring directions and how to analyze directions. And it turns out that I'll give you a bit of a historical background as to how I got into this problem and how Professor C.R. Rao was my inspiration for working on this topic. Okay, so I'll read something I wrote in connection with Mahalanobis, but I'll say, those titles there. Kaljampudi Radha Krishna Rao, C.R. Rao, Prachanta Chandra Mahalanobis, PCM, and the Geological Studies Unit, GSU we still call it, Geological Studies Unit. And I just scribbled this morning and I didn't have time to write it up here. But anyway, the year was 66, I said. And after dabbling on many theoretical topics like, I was looking for a PhD area to work on. And Dr. Rao suggested things like extending Kramer-Rao inequality to functional spaces and various theoretical topics. As we know, Professor Mahalanobis' broad vision for statistics included not just statistical theory that was being developed at what we call the Research and Training School, but all important applications to various sciences. Mahalanobis was very fond of saying statistics is the key technology of the 20th century. Of course, that was 20th century, but it still is. It is the key technology. And the Geological Studies Unit had several geologists studying and mapping the Godavari Valley in Andhra Pradesh, in remote parts of Andhra Pradesh. In particular, a geologist named Dr. Supriya Sengupta collected a large amount of paleo current. Paleo just means past. Current, flow of river. And paleo current data from the Godavari sediments, Gondwana sediments of the Godavari Valley, which seem to he collected this data about the flow of the river. I'll come to that as we proceed to my real talk. This is my introduction, my historical background to how I got into this area. And the claim was that the river has changed its course over a long period of time. And Dr. Rao, he approached Dr. C.R. Rao with his data, and Dr. Rao was astute enough to see that the usual statistical models and methods are not applicable when it comes to paleo current data involving directions. And this area needed deeper study. And so he sent that geologist over to me. I was, of course, looking for any nice, interesting problem. And so, under the guidance of Professor C.R. Rao, I then took upon investigating questions like, how does one compare several populations of such directions? River flow at one time versus another time. What's an optimal sampling strategy? Dr. C.R. Rao even sent me to Godavari Valley with these geologists to look at how they are collecting this data, how they should be collecting the data. That's how practical he was in terms of theory and practice. And so I worked with this geologist and we produced several papers, and I said a series of papers, and over a period of time we wrote a book. I'll refer to some of those things as I go, and introduce many statisticians in India to this field. In fact, India is one of the few countries where many people work in this topic called directional data. And the next new test procedures that we developed and their application to paleocurrent data from Godavari Valley not only solved some of the immediate problems that Supriya Sengupta was interested in. And Supriya Sengupta says in one of the papers he published that this whole episode greatly pleased Mahalanobis, and it is the reference to the paper. And such interplay between statisticians and scientists from other disciplines further strengthened not only PCM's convictions and vision, but gave ammunition to why such science units make, why are such units there in the ISI, Indian Statistical Institute? A question that was apparently being asked by the review committees at that time. So Dr. S.L. Jain of the GSU, Geological Studies Unit, he was the head of the department in that unit for a long time. He would tell me on more than one occasion that this interplay and work was instrumental in saving the GSU at the ISI from extinction. These review committees were saying, why do you have geology unit and a biology unit in a statistical institute? So Mahalanobis was very pleased that there was this interconnection that we established, and is partly my work inspired by Professor C.R. Rao under his guidance. Okay, now I'll get to my real talk about this area called directional data and what it is, why is it different, why did Dr. Rao send this geologist to me to investigate this problem, and then I'll tell you, it will be a very elementary talk because I know the audience is mostly students. So I'm going to tell you, as my full name, Srinivas Rao Jamalamadaka. I'll come back to this name at the end of this talk again. I'll tell you why. Okay, I'm at the University of California. University of California has 8 campuses. Santa Barbara is one of the top 3. And okay, I'm going to raise some scientific questions, various scientific questions in different fields of study. And then I'll talk about directional measurements, what makes them different, alternate measures. It turns out the sample mean, sample variance that we all use don't work anymore with such data. So I'll tell you what are the alternate measures, and I'll go back to the scientific questions, how the directional data relate to that, and I'll also talk a bit, if I have the time, a random walk problem and testing isotropy. And what's in a name? That's what I'll. Okay. Consider the following scientific. I'll pose a number of different questions from different fields. Did a river change its course over geological time? That was the original topic that Supriya Sengupta was interested in. And that has to do with directions, the direction of flow of a river. And is the ozone level in Santa Barbara, where I live, affected by the pollution levels in a major city like Los Angeles? Because the wind direction plays a role. And migration patterns of animals. For instance, we have these very pretty looking butterflies that come through Santa Barbara in thousands, tens of thousands over a period of time, and then in a particular season, and they move on. And the biology professor in Santa Barbara was interested in where do they come from, where do they migrate to? And that happens with bird migrations, and this is a big subject by itself. Is there scientific evidence to support the hypothesis of continental drift? You all heard of continents move, right? Is there some role for directional data in answering such questions? Is Earth's magnetic pole reversal a factor of fiction? Did you hear of this magnetic pole reversal? The north-south magnetic pole shifts, becomes south-north. And that doesn't happen every day, but it happens over a period of time. I'll come back to this. Directions play a role again in answering such questions. Is there a pattern to the epicenter of earthquakes? Okay, earthquakes occur in different parts of the globe, or is there a pattern to them on this top of the sphere? Is there a justification to the sociological theory that more people die after a major event in one's life than before the event? This is something very interesting. This, if you look at one's birth date as the landmark, look at people who die 3 months before the birth date, upcoming birth date, and the proportion of people who die 3 months after the birth date. You have to proportionate carefully. It turns out more people wait until their birth date is passed. That's sociological data, empirical data says that. And I'll tell you, is there a particular part of the day when more heart attacks occur? You see, I'm already introducing you to a 24-hour day cycle. This is the 24-hour cycle right there. And there's more heart attacks around 10:30, 11 in the morning, when perhaps there's the office time, people are in a rush and so on. So it turns out these are all empirical data. And I'll tell you, this is cyclical diurnal variation. Similarly, if a woman has to undergo certain surgery, what part of the menstrual cycle is a better time? Look at the 30-day cycle of a woman's menstruation. And that's a cycle again, it relates to directional data. Such questions which look very different, and I'll tell you how they connect, all of them connect to directional data. Is a company cheating on its taxes? Is a student copying an essay from another source? Like the Wikipedia article, you are asked to write an essay and you copy from somewhere. Can I tell if it is a copy? How far do the mosquitoes travel from the breeding ground, say a pool of water? Okay, these are all very differently looking questions. Recently, I have been collaborating with a person that some of you would know, a professor who used to be at the C.R. Rao Institute in Hyderabad, that's Soumyadipta Pine, he's at the University of Pittsburgh. We are now working on glaucoma. Glaucoma in the eye pressure increases, and what doctors do is to look at the intraocular pressure, and then they just say you have glaucoma and they give you eye drops or treat you. And we are looking at what are called optical coherence tomography data. This is about neuroretinal rim around the eyeball. There's a retina in the back, and how thick are the nerve fibers around it. So these are all technical terms. RNFL is retinal neurofiber layer, and this thickness around the eyeball, again I'm referring to a circular curves of some kind around the eye. And we are trying to see, can we use such more sophisticated measurements to predict glaucoma than just taking the eyeball, pressure of the eyeball. Okay, a common theme to all these questions is that empirical and statistical evidence for all these things come in the form of data, which are a set of directions. That's why my talk is called a matter of direction. Okay, in many physical and sciences, this is my introduction to you, geology, biology, ecology, I already referred to some of them. The basic measurements are quite often directions. Directions can be in 2 dimensions, just on a plane, or it could be in higher 2-3 dimensions on a sphere, or it could be in higher dimensional spaces. Okay, and for example, I'll give you a quick review of some of these ideas, and hope I'll get through most of what I would like to say. The direction in 2 dimensions, we all know how we can measure them as angles between 0 to 360, right? And they're called, if you take a circle, the length of the diameter, the radius is not important to me, the magnitude. Just the circle of unit radius would be fine. So you can think of an angle on 0 to 360, and so you can say, for example, wind is blowing in a northeasterly direction. What does that mean? Can you quantify this? And here is a way that circular data or 2-dimensional data, 2-dimensional directions can be represented. What am I writing here? This is, you can think of this as an angle theta. That's the 0 to 360 business. And the length is 1. Those are what you might call polar coordinates. Or you can think of the rectangular coordinates, cosine and the sine, x, y, right? That's how you can think of a direction in 2 dimensions, either as an angle or in terms of the rectangular coordinates cos theta, sine theta. And you can do something similar with 3-dimensional directions. I won't get too much into this, but the point is that in 3-dimensional directions, you all know, for example, Bangalore has a longitude and latitude, and those are 2 angles. And they tell you where exactly on the top of the sphere we are. So there are 2 angles that define a point on the surface of a sphere. So 2-dimensional directions are 1 angle, 3-dimensional directions may be 2 angles, or maybe in terms of the rectangular coordinates x, y, z. We all do this somewhere. So these are directional measurements, can be in 2 dimensions, or in 3 dimensions, or it could be in higher dimensions. Okay, what's happening? In circles, there is no natural 0 direction. What do I mean by that? In a circle, there is no beginning and no end, right? So where do we put our 0? If you talk to a mathematician, they say the true east is your 0. And if you talk to a geologist, which I often do, they say the true north is the 0. And they go measuring things going clockwise. And we measure things going anti-clockwise. So it turns out we'll get 2 different numbers for the same direction, right? So there's no natural 0 like on the real line. So that is the big issue. There's no ordering also, clockwise or anti-clockwise ordering. What was I saying here? The sample mean, sample variance are typical measures, and the standard measures. Okay, so here is my point. When I see, for example, the wind blowing in that direction or a bird flying in that direction, if you go east and go that way, is 60 degrees. If you start with the north and come this way, is 30 degrees. So whose number should I believe in? if you do statistics based on these numbers, you will get different answers depending on where the 0 is. So this is what I want to avoid. This is called invariance. I want measures that do not depend on where I put my 0 direction or which direction I go ordering things. Okay? And for example, here is the little example. If you have two birds flying in that direction 15 degrees and 345 degrees, and if I ask you what's the average direction of these two birds, that would be 180. 15 plus 345 over 2. And that doesn't make any sense that the average direction is this way. That's just the 180 degrees wrong, right? So the point of this particular thing is that the arithmetic mean that we all use points the wrong way. So it turns out that none of the usual things that we do, like the sample mean, the sample variance, the moments, the MGF, all the things that you do, t-test, f-test, the big packages that you use, they're all worthless when it comes to measurements which are angles. Okay? We need a new set of tools and descriptive measures corresponding to x bar and s square. So the point is, we have to start at the beginning. No sample mean variance will work. It's x bar s square business. And so I'm going to tell you quickly a couple of things and then move on to the scientific questions I raised. I'm not going to give a tutorial. There is a big topic now. There are books written on it, including one by us. Okay, here is what I do. It turns out if you have two angles, say one pointing in this direction alpha 1 and another pointing in that direction alpha 2, like the 15 and 345 I was mentioning. So the average direction should be measured the following way. Think of these as unit vectors. I pointed that as a polar coordinates. Length 1, but this is pointing in this direction, the other one is. Take the resultant vector of these two unit vectors. Resultant vector. You know, your scientific calculates anything, and you know what a resultant vector is. Okay, so that is the resultant vector R, and that is going to give me the direction of this resultant vector is a good measure of the average direction of these two. Again, what I do is, if you give me two angles, it can be more than two, look at the resultant vector of these angles, and that is the capital R, the resultant vector. It has a certain length and a certain direction. And the direction that it points to, one can show that it doesn't depend where your 0 direction is. It doesn't depend on which way you go, positive or negative. So that's a good measure. That's an invariant measure in the sense that I'm looking for. Not only that, you get another benefit from this. That is that the circular, the resultant vector points the right way. It depends only on the data and is immune to the so-called 0 direction. And not only that, the length of the resultant vector. If you have n points, if unit length each, the length of the resultant vector can be 0 up to n. Right? You can see if all the vectors fall on each other, you can have a resultant vector going all the way to n. So the length of resultant vector going from 0 to n is a measure of concentration of the data. So you see, I already get you two measures that replace the x bar and s square. What are those? The direction of the resultant vector and the length of the resultant vector. So we're talking about altogether different measures. Okay, so that's the tutorial. That in other words, when you have directional data, don't use your sample mean, sample variance, t-test, f-test. In fact, people in very respectable journals until 1960s, early 60s, people were using analysis of variance using f-tests. They were all rubbish in very respectable journals. They are not correct, because if someone was changing a direction of where the 0 direction is, they would all be giving you different answers. So there's a totally different measures that we should use. So I'm coming back to, I just told you what we should replace the x bar and s square with, but there's much more to the stuff. Okay, so paleo current analysis. Paleo current analysis is what this geologist Supriya Sengupta was doing. And so it turns out the direction of the flow of the river, you can get that from the sedimentary rocks, the rock bed. You can tell how old these rock beds are, sedimentary rocks, and which direction they point to the direction of the flow of the river. So he can tell me these rocks are million years old, and the river was flowing in a certain set of directions. So he was taking a sample from that. So that is what happened. Similarly, scientists working in ornithology, these the bird scientists, and they do flight of birds and where they're heading, and that's a big subject by itself. These are all, I'm pointing you to various fields where directions play a role, and every one of these topics I'm mentioning has dozens and hundreds of papers and books, ornithology and such stuff, where they have to use directional data because they are measuring the direction of flight of birds. And I said it's a matter of directions again. Earth's north-south magnetic pole completely reverses itself. I had a colleague in Santa Barbara who was collecting this data on the Earth's magnetic pole direction over a period of time. How does one do that? He was not alive for more than 60 years. So it turns out Earth's magnetic pole is preserved for us in certain type of rocks, igneous rocks. When the volcano flows and it's under the influence of the Earth's magnetic pole at that time, it preserves the direction of the Earth's magnetic pole. So we know the direction of the Earth's magnetic pole at that time, and we know how old the rocks are. So it turns out we did a lot of analysis, and its magnetic pole reverses itself on the average about 450,000 years, once every, and it takes a while to do that. And we may be in for one, because I said the last magnetic pole reversal is 780,000 years ago. And in fact, there are signs already, if you pay attention to this particular topic, there are some signs there is a slow migration going on right now, north-south magnetic pole reversal. Paleomagnetic directions can be used to compare continental drift evidence and so on. Paleobotany is one way. I'm talking about the continental drift. That can also be assessed through paleomagnetic directions, and they provide further evidence too. I'm trying to come back to the questions I raised, and I'm saying in each of these questions, either you are dealing with two-dimensional directions or three-dimensional directions. Nevertheless, directions. Diurnal variations, time of heart attacks, time of taking a medicine, that is on a circular data. On a 24 hours can be thought of as a circle, and then timing of a surgery. This is a big subject by itself, chronobiology and chronotherapy. People say when you take your medicine is as important as whether you take it. Certain medicines work best in the morning before you have medicine, food, and some work after the food. So the question, this kind of questions, when should one do surgery for, related to the menstrual cycles, birth-death cycle. This is the question that I raised. If the birthday is there, when does the death come? And these are all, I'm saying there is a lot of things that can be related to circles and spheres and directional data. Okay, what is this about? Oh, this is, I mentioned about, is someone cheating on taxes. Okay, it turns out, I don't know how many of you heard of this. This is an interesting topic. This is called the first significant digit phenomenon. First significant digit phenomena. What is that about? If you look at a large set of numbers, look at the first non-zero number. It can be 1 through 9. No, 0 is not counted. Okay? So how frequent are these numbers 1 through 9? One would expect they should be equally frequent. Not so, not at all so. In fact, there's a guy named Benford. There's a recent book on this topic. That guy Benford. There's a book called Benford's Law, and there's a big fat book that recently came out. It turns out there's a lot of theory behind ergodic theory and so on that can be used, but it turns out that number 1 occurs 6 or 7 times more frequently than 9. This guy Benford, what he did was he pored over a lot of Reader's Digest magazines that he had. He looked at every number he saw on every page, and he said, how many times is 1 coming, how many times 2? And they were not equally frequent. 1 was occurring much more frequently than 9, for example. And it turns the numbers, first 3 numbers, 1, 2, 3, is 60% time. It should be 1/3, right? 9 numbers, 3 of these should be 1/3, but it's 60%. So that's called Benford's Law, and there is one can find if someone is, making up numbers instead of natural occurring numbers. okay, using this Benford's law. What has that to do with circular data, you might ask? I have a small proof as to why circular data comes in, but I will skip. But you pay attention to this. First significant digit is k with probability log k plus 1 over k going from 1 through 9. For example, this is logarithm to the base 10. So if you look at log, first significant digit being 1 is log of 1 plus 1 over 1, which is log 2. And that's a big number compared to log 3 halves and so on, so forth. Okay, so that's the, I think I won't get into the proofs. Texts, I said, it says are the two texts similar? It turns out this is called semantic text analysis. You can look at the text and reduce it to a unit vector of some kind in high dimensions. What am I talking about? Look at the frequency of words that occur in the text. Okay? And look at, suppose the dictionary consists of k words. How frequent are these words? Say frequency of word 1 is f1, frequency of word 2 is f2, f1, f2, fk. So it's a k-dimensional vector. Reduce it to a unit vector and put on a k-dimensional sphere. You can also do with a similar, another text like this, g1, g2, gk. So there are 2 points on the surface of a sphere, and you can ask how close are these 2 points. That tells the similarity of the text and so on. There's a whole bunch of things. Anyone interested in any of these topics, I'm around. I'll give you a few references if you're interested in studying more on this. 2 texts can be compared by taking the angle between the cosine angle between this. So what am I going to conclude? If the 2 texts are very, very similar by a significance test, I can say this guy copied from this place. They are so similar that they must be a copy. Okay. Similarity. It's again a matter of direction, I said. Here is something very interesting. You see, in circular data, if someone comes to you and gives you a set of points and a circumference of a circle, you shouldn't immediately jump and calculate the resultant vector in this direction. That's what I was suggesting. We should first of all ask, is there a preferred direction? Is there any, suppose birds are flying in different directions. You should ask yourself, do they have a preferred direction? Only then does it make sense to calculate a mean direction. If that question doesn't arise on a line, you calculate an x bar anytime you see some data. But on a circle, before you jump to calculate the mean, you should ask, is there a preferred direction? Otherwise, it's isotropy. It's called uniform distribution. If birds are flying all over the place, they don't know where the hell they are going, so we don't know how to say the mean direction of those. So that's a very important question. Okay, and here is some interesting story I wanted to connect it to. A fully drunk starts at, I'll skip all the story, and it's called a random walk. It's called Pearson's random walk. I'll connect his name to this. So what is going on? You have a drunk, for example, starting at point 0, walks a certain length, takes a random twist, and walks a certain length, takes another random twist. Okay? And then after walking so many steps, I'll do a picture here. This is more easy. So what's going on here? You start here, you walk a certain length. This is a random twist. What do you mean by random twist? Any number from 0 to 2 pi. So he might actually turn right back and come back to the bar again. Okay. Or he might go take that twist and go that way. So if he goes n such steps and ends up at this place, final place, what is the length of this? Where does one, the distance between the beginning and the end of n such steps? This is called a random walk. Why is this of interest? Because people think mosquitoes, when they start from a breeding ground, they go certain this direction and they seem to buzz around and you don't know where the heck they are going to go next. So they take a random twist. So they go another random twist and so on. This is what people have theorized and have connected, and that goes back to an interesting historical story. Sir Ronald Ross won a Nobel Prize in medicine for connecting malaria vector to mosquitoes. He is the first one to have connected. I usually tell the story saying Ronald Ross lived in Hyderabad because there's a museum in Hyderabad in his name, but other people say he lived as much time in Calcutta. So Calcutta and Hyderabad are his main residences. He's a Britisher, but he lived in India. He got a Nobel Prize. He got a Nobel Prize for connecting malaria to the mosquitoes. And so mosquitoes buzzing off in random directions. So what happened was, in 1940, he asked Carl Pearson, he is the big man in statistics before Fisher, around Fisher time maybe, and then he asked Pearson, how far do the mosquitoes go if they were randomly twisting and turning and going in different directions? And Pearson thought about it for a while and didn't know the answer, so he published it as a question in Nature. Nature is as good a place to publish problems, I guess, in those days at least. So Pearson tried his hand at this for a while and posed this problem in Nature. What is the problem again? Mosquitoes, starting from where they are, how far do they go in certain number of twists and turns? All right? Okay. This is known as the Pearson's random walk problem. Even though he neither came up with the question nor the answer, I say. In this sense, question came from Ronald Ross and he didn't have the answer in any case. So it turns out this kind of a random walk that I'm referring to comes up in polymer chains and physics and a lot of different areas connect to this particular random walk issues. Anyways, answers, the real answer actually depends on a lot of mathematics behind, Bessel functions and so on, and I'll skip the details, but it turns out here is a short summary in terms of quantitative stuff. If you take 100 steps of unit length, 1 foot each, what were we talking about? A mosquito starts here, goes 1 foot, turns around, goes 1 more foot, 100 feet. If it is going straight, it should go as far as 100 feet. If it has any sense, it can go 100 feet. How close can it be to where it started? 0. So it can be 0 to 100. But it turns out the 100 steps, 95th percentile of the length that you can go is 17. What does that mean? I mean this. You all know your percentiles. The probability that R exceeds 17 is only 0.05. 5% of the mosquitoes go beyond 17 feet in 100 swings, right? So otherwise, that's why the mosquitoes stay close to the pool of water, most of them. Okay, so that is the answer to the question, and this answer demands more. There's a lot more interesting story. Rayleigh gets involved in this answering this question, and so on and so forth. Raleigh's distribution and so on. But here is some interesting story. I said in California, where I live, the police that stop you when you are driving a car, they ask you to get out and walk a straight line. And I'm saying if you can walk more than 17 feet in 100 steps, you are perhaps not too drunk. Okay. So in other words, if you have any sense, you will go 100 feet, right? Anyway, that's the joke. Okay. Now, here is the L.V. Prasad Eye Institute. That's where this glaucoma business. This is something more recent we are doing. We have data on retinal neurofiber layer thickness, and we have 5,000 such circular curves. And the question is, can we use this circular curves data to predict glaucoma? In other words, can we say with age, some glaucoma results more and more frequently, or with gender, things like that. So we have covariates and we have a lot of data, and this is what we might call functional clustering of curves. Okay, and that's what we are doing, and we are going to write a long paper soon, and that's that's how the jumble of curves look like. This is basically your eyeball is in the center, and this is the thickness of the nerve fibers around the eyeballs. And the question is, how do we tell from here which are the curves that corresponds to males, curves correspond to females? Do the clustering first, do they connect to gender, to age, to other covariates, and so on. So it's also a matter of direction. So that's how the Pine contacted us. We are working with somebody at the L.V. Prasad Eye Institute in Hyderabad, and we have a huge amount of data, and we are trying to figure out whether these curves have a story to tell in terms of glaucoma occurrence or potential for glaucoma, things like that. Okay, now you have no doubt noticed my long name, Srinivasa Rao Jamala Madaka. And I used to be known as Jamala Madaka Srinivasa Rao, or simply J.S. Rao, like BLSP Rao here. Our family name we write in the beginning in Andhra, right? B is his name, C.R. Rao, C is his family name. And when I went to USA, I changed my name from...
Yes. See the place where he was born, or his ancestral
It is oftentimes, it has, I don't think there's, Jamalamadaka in my case, there is a town. There is a town, yeah.
It's a family name also, but
right.
it's a place name also.
Is that true always? Not necessarily, there's no place where Bhagavatula, but any case, but yeah, oftentimes it is. But the point is, we write our family name in the beginning. Whereas in USA, when you go there, they say first name, middle name, last name. Last name is the family name. So I changed my name from this to that. And I'm often asked this question. Since we are discussing directions and circles, I say here is a direction that explains. If you start with the true north, Jamalamadaka Srinivasarao. If you start with the east, it becomes Srinivasarao Jamalamadaka. And I say it's a matter of direction again. Okay? So even this is a matter of direction. Okay, now I'll stop there. I'll refer you to a book that we wrote, which we are actually revising at the moment. There's a Professor Rashid Sengupta, who is at the ISI Calcutta, who is just retired, I think. We are revising that book. There's another good book called Mondrian Juk by Directional Statistics. And we have an R package. Perhaps most of you use R. Don't use the regular R packages. There is a package that we wrote, one of my students wrote with my help. It's called CircStats, Circular Statistics. It tells you how to calculate the resultant vectors, tests that correspond to this, and things like this. This is an online and free package. Incidentally, this is something that, I gave a similar talk at Uppsala, Sweden, 4 or 5 years back when I was given an honorary doctorate. And this talk is more or less recorded by them. Is a video of that presentation. Not that I want you to copy this. If you Google for it, you will find a presentation of this kind. Okay, so that is where these are the references. I think I'll stop there.